Thank you, George. That was great. And I'll invite Josh and Kevin to come back up, and we'll have an open Q&A and discussion. Remember to raise your hand if you want to speak so I can bring the mic in so we can make sure to loop in the recording.
So I just wanted to congratulate you, George. Like the milestone of getting to first flight and really pioneering the way, it's fantastic. So thank you for everything that you're doing for electric aviation. My question is more on the operational side looking forward, and I don't know, this may be a little early to answer this, but it's two parts. One is, have you gotten to the point where you're starting to do stall testing of the Electroflyer because it's going to be used in a training environment? And then two, I'm kind of assuming here, so you can correct me if I'm wrong, that your wing has a lot of laminar flow to achieve these very high LRDs. By the way, getting to over 20 with a fixed gear aircraft, amazing. So I'm wondering if you could just comment, are you planning on having special training procedures of like making sure that that leading edge is clean of bugs? I remember when I was training, you know, there's bug splatter on the leading edge of the wing all the time, and if you're imagining that you're going to have to do some special things for flight training with a very clean airframe to ensure that you maintain good stall characteristics and all that sort of thing.
All right, so Carl was talking about the LRD of the wing and the laminar flow of the wing, the efficiency of the wing. It's an anti-spin wing, Carl, so the approach to stall is very, very soft. The aircraft, we'll be demonstrating the stall with the yaw and so forth. As you know, it's not required in pilot training anymore to have spin demonstrations. The instructor pilot requirements still include spin demonstrations, but the aircraft itself is built for the pilot training syllabus, and yes, there is some sensitivity to bugs or whatever you might have on the leading edge of the wing, but that's pretty much part of the normal walk around of a typical sortie with the instructor and the student walking around checking the integrity of the aircraft. And of course, as you point out, leading edge and things like that.
Two questions. For George, I know with your EP packs, it's quite similar to what's being used in the X-57 Maxwell program at NASA. And the program manager stated a couple of weeks ago that they were going to have to be doing some preconditioning for the packs, and he expected that there was going to be some temperature limitations during their flight tests just to control the battery pack temperature. And I'm wondering what you've been thinking about in terms of how that plays out in operational use and in hot places like the Aspen Flying Club and others.
Yeah, thank you. The battery packs thus far in flight tests have not experienced any temperature elevations. In the X-57 Maxwell, the battery packs are located inside the fuselage and they're not ventilated or cooled. In the Sunflyer, we have an active cooling program. We've got blowers and air going through there. So the Siemens motor is a liquid cooled. So we've got lots of air movement and sensitivity, awareness, if you will, of the temperature environment. Mostly around the motor controller, but we're watching, of course, very carefully the battery packs, which are well qualified and temperature tolerant, I might point out. But we've designed the cooling of the batteries with that airflow for that purpose. Thus far, in all of our tests, no problem, no elevations. And I know we all know that here because we're all fairly familiar with electric propulsion, but generally speaking, the power required for any flight segment is multiples less than when we're recharging. The batteries are stressed during recharging much more than they are when we're flying. Even in takeoff, it's such a short duration relative to the air work that we're doing and the rest of the flight syllabus or training segment, that actually most of the stress occurs during recharging. So we have that's where we watch it, the temperature for the packs.
Okay, thank you. And I had one comment for all three of you. Is one of the charts that was shown kind of showed the Cafe Foundation kind of at the center of a lot of activities. And because the Cafe Foundation has kind of a worldwide reputation for flight testing and verification of data, I'm wondering if there's been any thought to involving Cafe in some of the verification of the performance of the vehicles that you're thinking about making.
No, absolutely.
Absolutely. I think that having a centralized body, and it could be the Cafe Foundation, which can be trusted, that a mark of trust where people who maybe aren't as in tune with the progress within the industry, but can look at that mark and say, somebody has done the due diligence, a third party has vetted this out within the community who understands this. I think that that's essential, just from a public acceptance, forget about the certification side. And so I think that some organization that would be required, and I would, of course, defer to the organization.
FAA has been looking at over the last year to serve that role in the industry as we did many years ago in the experimental industry. So I'd love to get any input from anybody that's interested in that. I think the next step for us is to put together kind of an industry advisory committee to frame that out. But that's definitely from a vision perspective and mission perspective, something that kind of falls squarely into what CAFE is doing.
Yeah, my question for George related to your battery, because it is the heart of the solution.
Sure.
Can you give some details about the weight of the battery and the replacement cost?
On behalf of?
No, going to George. Talking to George, sorry.
Josh.
George, can you give us some details about your battery, the weight of the battery, of the 73 kilowatt hour usable battery, and the price of the cost of replacement?
We're using inside the EP Systems battery pack, we're using the LG Chem 18650 lithium ion cell. That's 260 watt hours per kilogram. 260 watt hours per kilogram. MJ1 cell, 18650 lithium ion. One of the great things about EP Systems is the traditional weight ratios of cells to actual packs, probably industry leading. And again, I'm not at liberty to share EP Systems data. Please take it up with them. They may be happy to share that or not. I'm not sure. But I would certainly say, in our experience with Dow Chem and Panasonic and many others, EP Systems is absolutely leading the industry. So, very light. But the ratio of structural and computer weight, the battery management system weight, is certainly industry leading, no doubt about it, as well as the safety, I would say.
And the cost?
I don't know if we can release that either. It's well within the $289,000 cost, of course, of the airplane.
That's a nice broad question.
Yeah, I'm sure we all are representing different parts of the industry, and certainly I would love to answer that, but we need to protect our friends. As they collaborate with us, we also have to be careful of not giving confidential information.
But it is the heart of your power.
Yes, indeed. And absolutely. And that I would say with great confidence that covers the battery pack replacement in that roughly 3 to 5 year time. So you can kind of compute with that.
Yeah, this is following up a little bit on George's saying the batteries are more stressed during recharge. And it's really for Josh. I kind of get lost on all the socket things, but one of the things, I think it was at Uber Elevate, was a liquid cooling of the batteries when you're charging them. Mm-hmm. Do any of those
So none of those do, and
Connectors.
it would be a next generation that could still have the same electrical interface and CAN bus communication protocol with some sort of augmented, tubes for liquid cooling if you were going that way. To be honest, I am a little reluctant to add that complexity and weight to the aircraft, and I'd say things like just more active air cooling is probably sufficient. So the Alpha, for everyone's reference, has air-cooled battery, it's no secret, and the fans are just working overtime when it's charging. So it's keeping the battery cool while rapid charging at 1C. You get basically 45-minute charge to be able to fly again. To be honest, that's more than fast enough for us. So, flight school, we find the typical ratio of flying to ground school is at least 1-to-1, sometimes even 2 times on the ground versus 1 in the air. So by the time you do your pre-flight briefing, get in the plane, go for a fly, come back and do your post-flight briefing, the aircraft can be charged in that post-flight briefing, hand over to the new pilot. So for now, it's actually not a bottleneck. Charging is not a bottleneck. And to be honest, George's aircraft has an even greater ratio of flight to charge time, because that 1C charge is kind of what the battery's like. Anything faster and you're really kind of hurting them. Anything slower, you're taking a little too long. But with, say, a third of a C discharge as opposed to 1C discharge on the Alpha, you've now got 3+ hours of flying for every 45 minutes of charge. So the flight to charge ratio on the Sunflower is substantially better. So I don't foresee it needing liquid cooling. The regional thin haul might eventually benefit from that, and that's maybe you can add to that. But
Yeah, I would love to jump in there. So in my talk, I was describing this interplay between the technology viability and the market requirements. And what we've heard from the customers who would actually be operating thin haul electric aircraft is that the turnaround times they require cannot be met with an on-aircraft charge. In order to meet this near-term viable solution, it would require a swap. And so there are some opportunities that come if you look at battery swapping. For example, you don't have the high charge rates, so it maybe mitigates some of the thermal system weight. Similarly, you can optimize cells that might have that lower power capability and optimize more toward high energy density, which there are chemistries out there which meet those types of requirements. Now all of a sudden we've got a little bit more, let's call it operating, range of the flights. And then similarly, when we think about, again, the iterative approach and architecting a system which will scale with the industry, the batteries which you are, for us, considering swapping, you expect to be replacing these battery packs over the life cycle of a vehicle, right? The battery replacement costs are already part of the cost model. It would be foolish to go down this path if you didn't think through that and make sure that you were economically viable with that element in there. Then you consider, when I am replacing the packs, bringing new technology in, the capability of that packs. It kind of plays quite nicely with this off-board charging that we are looking at, which really seems essential for the thin haul and regional market. You could do it at night, and then you don't have the peak costs of power. Again, there's quite a few benefits there. Comes with its challenges, of course.
Hi, Roger Gerson. I've met a couple of you. George, you and I have talked on the phone at least once, maybe a couple of times. Previously with Bramo, now with Cummins. Just going to pile on here since a number of other people asked battery questions. I warn you, I know a little bit about batteries. It seems like all three of you guys are using the EP Systems battery in your project since that image appeared in all three presentations, I believe. And I think you all three agreed you're not cooling the battery in these applications. Is there a provision to heat the batteries to get them to operate well at lower temperatures?
Well, I'll clarify, we don't yet use EP Systems batteries, but they are becoming an industry standard, and credit to George's work with them and NASA's. Obviously, Pipistrel made their own battery using their own choice of 18650, which I can't disclose, but I can tell at least they have been open that it's an 18650 standard. We do a lot of high-powered stuff, VTOL stuff, prototype stuff that we're not allowed to show you, and 18650s would really struggle, so we don't use 18650s for most of our VTOL ducted fan prototype work. It's mostly polymer cells, to be honest, because they have the power density, they can deliver the power. And then for really safety-conscious applications, we use phosphate cells. So we kind of pick and choose based on the need of the application. Safety with phosphates and abuse, you can thrash them, rapid discharge, recharge, cycle them a lot, but they lack the energy density. And you can get away with less cooling on those, whereas the polymer cells, you can deliver a lot of power and reasonable energy density, but they do need cooling, especially in charging, but fan cooling is generally sufficient. And then the 18650 cells. Now Tesla use liquid cooling because you can justify the weight in a car and a vehicle to have that really actively thermally managed. But I foresee that maybe the thin haul, but I see most light aviation getting away with air cooling as long as you're proactive about it and have fans that turn on and off and make sure there's enough flow. So that's, if that answers your question.
I'm going to re-ask the question. So
Okay.
yes, I understand the issues around cooling and
Yes.
that we've got some good options, particularly air cooling would be an effective strategy in these applications.
Yep.
My question is about heating in order to
Okay,
get
sorry,
good
yes.
performance out of the battery at low
I
temperature.
can address that. The way we do pipistrel flights first thing in the morning on a cold day is you just warm the batteries up through either a fast charge. So by actually putting it on a fast charge in the morning, it's warm enough to go flying. And or if it's already charged, just by running at a low power setting, you can warm the batteries up naturally. So
Okay, I would caution you against that strategy, but
Yep.
you'll figure that out. I'm wondering what the other two gentlemen are doing with battery heating.
So,
Yeah, from a very, very cold temperature, say University of North Dakota, some preheating is called for, yeah.
and the way that we're looking at this is, again, in that interplay between technology viability and market requirements. There are quite a few features that are quite essential for certain markets, but not essential for others. In our iterative approach, we've pushed heating off to the side, that the initial customers, these airlines that we're working with, don't operate in environments where that seems to be a requirement for them. And while we expect those types of features would need to be included in order to capture the broader market, we're really focused in on demonstrating the value proposition in other areas.
Thank you very much.
So I am assuming that the 30-minute reserve is being met for VFR flight, staying above the 20% state of charge for the battery system. Would you allow the pilot to have access to that charge below the 20% state of charge in an emergency situation or even in the 30-minute reserve?
So,
All three, I mean.
it seems best practice would be to not have pilots going into those battery reserves, right? That's for system safety. So I would recommend, if you're having those FAA required reserves on top of the system safety reserves. Now, does it have to be a 20% buffer there? In that measurement, maybe it's between 10 and 20%. But then I would also imagine that if it's a safety of flight concern or saving somebody's life, or maybe keeping the batteries from overheating, giving somebody the ability to pull power, but also really deeply understanding what that means to the battery packs. Especially, you don't want to trigger other failing modes that would lead to a more dangerous situation. And so that gets into the details of the battery pack and discharge properties at low state of charge. I don't know what other groups are doing there, but you really want to avoid going too hard at the bottom.
you include the 20 in your reserve?
Yeah, I would argue that 20% is kind of an older technology level. We're much closer to 10% and even 3 to 5% before you're damaging cells and things like that.
Yeah, so
And they're holding state of charge much longer. That cliff is really moving over to the right on the graph.
especially in lower discharge rates like the Sunfire 0.3C discharge. I can answer it from Pipistrel's pilot operating handbook point of view, in that they do include the full energy as inclusive of reserve, but we never fly below 30%, and that's because that is our reserve. So So for instance, in our flight logs, we're typically landing at 35 to 40% energy remaining, and that's about a 45 to 60-minute flight, depending on how aggressively you're flying the aircraft. So, you know, circuits versus stalls and things like that. So we've never even gone below 30%, because in our mind, that's the half an hour reserve you're leaving. But that is getting the battery all the way flat. And they say the last 5% is where you're damaging the cells. So if that answers your question, that I suppose they are including that 5% in the pilot could use that and damage their cells for the sake of saving the plane and whatnot, but you're already like, you know, you've spent tens of minutes trying to find an airport by then. So I'd say that in that regard, in light sport, they're kind of including that in the reserve.
Okay, I have two questions here, one for Josh and then one for Kevin. Josh, in your presentation regarding Trek and ducted fans, I've done some reading on early work with ducted VTOL aircraft, Piasecki Air Jeep, the V-22 Bell, and I understand that historically there were challenges with ducts in gusts horizontally, and also challenges with drag in flight. And I also spent some time with Urban Aeronautics in Israel in November doing a cover story for Vertiflight, and Ureli has a different perspective on ducts. So I'm trying to understand how do you take the ducts that you're working with and solve some of these historical challenges that were there, either in horizontal flight with a duct that is facing downwards, or in, well, I got it wrong, in vertical flight.
And horizontal.
You understand what I mean?
Yeah,
Okay.
so
the duct configurations, either when you're taking off and you're in a gust situation, or if you're flying forward with the duct,
Yeah.
how do you address the controllability issues that
Sure.
historically existed?
So a good example is the Hiller flying platform, single duct.
Yeah.
Right, that was self-stabilizing to some extent. You did need rate damping, or a human doing the rate damping, but the attitude was self-damping just by nature of how much pitch back force that duct produces. And they could lean. They just couldn't tip it, because aerodynamically it would level itself back out again and it would limit the maximum forward speed. With a multi-rotor, like a 4 or more rotor aircraft, you've got more than enough control authority to push through that and actually get to those higher speeds. And then obviously all the way to horizontal, and then it's a different aerodynamic structure. People like Urban Aeronautics have more focused on the hover efficiency, because it's predominantly used for hover, and they're not really looking at transitioning it. They're actually flying it horizontally, and then you do have some significant drag considerations. Addressing the high speed one, like the V-22, fantastic. The Bell V-44, sorry, to clarify, the Bell V-44, which is a 4-duct tilt rotor, was a fantastic aircraft. They actually praise it as one of the best, most manageable aircraft to fly, like the easiest VTOL to fly in the history of VTOLs, and with minimal augmented stability, because they had the differential collective pitches to get that pitch authority out of the moments. To get back to answering your question about forward speed, though, they were trying to fly quite fast. There was an ambition there to have a high-speed VTOL, and then you've got some optimization trade-offs. I won't go into modern-day details, but certainly the work we're doing through Aerospace is proving that you can optimize for high speed, and there's some things you can do cleverer now with electrics as well to really optimize that. But there's always going to be that trade-off with hover and high speed. But I actually think it's a better compromise than an open prop in hover and high speed. Certainly a fixed pitch open prop in hover and high speed is much more compromised on efficiency these days.
And in terms of the issue of gusts?
Well, no, to be honest, that's a complete misunderstanding of ducted fans. A high disk loading ducted fan with a sharp Bell inlet radius does have issues with gusts like the Honeywell MAV, because if the gust comes and it detaches the Bell inlet and you actually are stalling part of the rotor, you've got this sudden change in pitch authority, and it's all these tiny vanes trying to do all that stability. If you've optimized that right for the typical operational envelope, you'll have attachment all the time. You've sort of you're basically enforcing the flow into the fan, so that the fan doesn't experience the gust. The fan only experiences what can get over the lip. So we can optimize for gust tolerance in these ducts, and that's what Trek have focused on, is the compromise, and it's a very delicate balance, but the compromise between hover efficiency, which theoretically is a nice big Bell inlet, forward flight, which is a much narrower, and if you think about it, all commercial airlines have ducted fans. They're just optimized for the 99% of high-speed cruise, right? So you've got to make that trade-off between that converging duct for high-speed cruise or divergent duct for hover, and the trade-off between the two.
Kevin, question for you. In terms of the short-haul, in a sense, commuter market that you feel that you can stimulate with your re-engineering programs, what kind of reduction in DOCs are you likely to see, such that you can get the fare to a price point that's attractive to pull people off the road? I mean, I guess that's I come out of the commuter airline, regional airline business, so that's what I'm curious about. What you're trying to do in terms of reducing direct operating costs.
Yeah. So there are two factors to this. One, which is the assumption that it'll be a direct drive into reduced ticket prices, and that we'll be pulling people off the road. I kind of fundamentally agree with. I believe somebody said this yesterday. It's not going to reduce congestion on the ground. It's not reduced because that's a completely different system. You pull a car off the road, at least one will fill that spot. So I would call into question anybody who says that these solutions solve traffic. However, connecting communities with affordable air travel, the question is, okay, which communities and what does affordable mean? If we were able to just operate at the same, those flights. I mean, direct operating cost, specific to your question, reduces to between 75 and 90% of the fuel cost. Maintenance, it depends on how you bucket things like battery replacements. That's what we're conservatively saying, 25% savings there. We anticipate maybe greater than that, but again, as a company, we're trying to take a realistic, conservative approach. We've mapped out the relative direct operating costs, and the airline operating costs are like your per passenger or per seat mile. While some companies may claim you can get under 10 cents per mile, I think those are dangerous statements. Certainly, I think if you're comparing against, I'm going to have to pull the numbers, you're looking at dropping it well over half, if not down to a fifth, of what the direct operating cost is for these operations. We haven't priced out the ticket prices with these airlines yet, but the key would be that, I mean, in context, the essential air services subsidize like $300 million per year, which is roughly half of NASA's air R&D budget. If we could just kind of hit that market just a little bit, I mean, that's all fuel price. That's all just fuel subsidies. If we can offset that fuel burn, if we could serve those markets or reopen those short routes, I think even a modest, like let's call it half direct operating cost would open up kind of this elasticity in the market.
And I'll make this just one last thing. Mm-hmm. Is the re-engineering viable for something like a seaplane?
So seaplanes are a bit of a challenge, right? I've talked about battery swapping. That's the challenge on a seaplane. It could be. We'd really have to look at the operation. So for example, if you look at Kenmore Air up in Seattle, this is one of the airlines we've been talking with. There's a question on when that makes the most sense. It is a more difficult, unfortunately, because there are a lot of them, and it would be a wonderful market to hit first. It is a slightly more difficult optimization that requires additional features, kind of tying back into this iterative approach where we're baseline ground operations first. But absolutely, we do think that for some airlines that don't need the quick turnaround time, where we would not have to be pulling large battery packs off of these planes over water or designing new docks, then it could be viable in the future. Yeah.
I can probably add to. Yeah.
I'll also say, depending on the timeline, and this was kind of watching out for growth areas in the market and tying that to technology. Let's say that it's 5 years or 10 years out before that makes sense. well, then that calls into question whether the retrofit is the right application, or if you should just go after a new build TC. Right, and what we've made a decision as a company is to not make those bets right up front. We still think it's kind of early, but we can do meaningful things and prove out value propositions all along the way, hitting it when it makes sense. Sorry.
That's good. I was just going to add last thing with air travel over water is substantially more efficient, electrically especially, than boats, right? So not just energy consumption, but time, right? So Ronest Air Taxi is one that we've gotten involved with. It's a 12-minute Cessna flight, and that's currently more expensive than going by boat because of the cost of those Cessnas. But you replace it with, Sunflowers, you've now got a substantially reduced cost flying there much quicker than the boats. You can get more people in the air, and then there's definitely a cost saving by flight versus sea travel.
Okay. If we don't stop now, there will be no break.
Yeah.
Thank you so much. It was a great discussion, and thank you to this panel for being up here and sharing your wealth of information with us.